Hello, everyone. Let's get started. I'm really pleased to introduce our special seminar speaker today. First of all, don't know me, I'm Allison Okamura. I'm a faculty member in mechanical engineering, and this seminar is hosted by the Stanford Robotics Center. Thank you for organizing, especially the HACO in the back there. So I'll give a little introduction to Harry. Professor Harry Asada is the Ford Professor of Mechanical Engineering, and he's Director of the Britt and Alex the Arbaloff Lab for Information Systems and Technology in the Department of Mechanical Engineering at MIT. He specializes in robotics, system dynamics and control, and biomedical engineering, and has done lots of amazing research over the years. It seems like his most recent interests are Koopman operator theory, which I think we'll hear a little bit about, assistive robotics for older adults, supernumerary robotic limbs, and also multi-cable manipulation. He has won too many awards to mention, so sorry, Harry, I'm not going to list them all. But I'll just say on a personal note, for about the past maybe 4 years or so, we've been collaborating on grant proposals, some successful, some unsuccessful, but also some really great students between our lab have collaborated and had some really exciting results. So working with Harry has been such an amazing learning experience in terms of his creativity and interest in really making real-world applications for robots that help people. But at the same time, you can do Koopman operator theory. So he's a full-scale engineer in terms of going all the way from theory to great designs and implementation. So it's been really exciting to work with you, Harry, and I'm looking forward to your talk.
Well, thank you, Alison, for a kind introduction. So I'm Harry Asada from MIT. It's a great pleasure being here and doing a talk at the Stanford. So I love robotics, and many of you are really passionate about robotics for maybe different reasons and interest. And in my case, the best part of robotics is kind of interesting interplay between robotics and the human. The human is a metaphor of robotics, and we gain lots of new inspirations and exciting ideas from the human. So that the human inspired robotics, at the same time, we build something, and then that exhibit what we call the dexterity or intelligence. And that kind of stuff is built upon the very well-defined component to give some kind of the impact and insight into the broad aspect of human studies. So to me, the intersection between the humans and the robotics, rich materials existing. And then that actually motivated me in doing the robotics research for several decades. When I was a graduate student, how can I move? Okay, when I was a graduate student at Kyoto University in Japan, in 1970, never mind the year, I'm disclosing my age. At that time, the robotics, the field of robotics it's infantry. So there's not much the tangible physical entities that we feel this is the robotics, other than the kind of old hydraulic industrial robot called the Vasatrans and Professor Hanafusa's lab, where I was belonged to. So and also there's not many papers to read, and absolutely no textbooks on robotics. So it turns out that my textbook on robotics is my hand. So I'm just looking at my hands every day and observing some amazing functions that we can actually find and try to explain what the principle behind it. And hopefully this one can be transferred to the engineered machine that's a robot. So that's when I came up with the ideas on the glass stability. And that was initially my master thesis at the Kyoto University. And this is to define some sort of potentials associated with the mechanical things that interact with the object, and then that create the kind of a potential curve up and down. And that's and also depends on the shape of the object along with the robot hand itself. And if you plot the isopotential curve on the after pose, position, the orientation of the object, you see some nice actually local minimum here. This may be a good point because any deviation from this point create the restoring force. So that actually means the stable grasp. So that's actually a simple explanation. At the same time, just several years after that, and I found that a very beautiful doctoral thesis by Professor Usama Katif, and then he also used the potential functions for totally different clever use. Now, implementing the stable grasp or this kind of hand manipulations based on the compliance with matrix, I had the troubles because it's hard to generate control the torque and the force on the fingers. So I came up with this actual design. This is the first serial elastic actuators, and actuator here, and then the fingers and hands are here in between. We have a coil spring, and by measuring the torsional distortions of this coil spring, we can get the measurement of the torque transmitted, so closing loop out of it. Now, human-like actuations are so important, and when I moved to Carnegie Mellon Robotics Institute, I just happened to find a little articles talking about the new type of high torque motor, and at that time it's kind of emerging technologies, rare earth, submarine cobalt magnet producing 42 megagauss Elsted magnetic strengths. And that was actually a big, groundbreaking the things. Together with the high power MOSFET they're getting available, so we can drive the large current into this. That allows me to develop the first direct drive robots, all 6 DOF. It's a direct drive having no gearing, and it's so high, no backlash, and then the pure torque controls. And then that was immediately commercialized by Adaptive Technologies and Sunnyvale, I think. I just forgot the name nearby. And then this one spread out to many manufacturing sites. In Japan, Yaskawa developed the direct drive robot for clean room applications and handling the on a wafer. This is a clever idea because direct drive doesn't produce any particles or the dust from the gear meshing because there's no gearing. Well, going to in 2012 at MIT, around that time I've been supported by Boeing's for about 10 plus years. And then I had a chance to learn at their manufacturing site. This is the final assembly of a wide body commercial aircraft. And to see those people, they are working either on the ceiling or the ground. And the kind of work is not good for the human. The human body is not designed for doing something near on the floor. So this is motions and this is Boeing 767 cargo space assembly. You have to take this posture the whole day long. It's nice if you have extra arms holding your body, right? Because the two of your arms and feet when you're doing this, right? Yeah, and then this is later, Department of Energy provided some grant to develop the assistive machines as shown here. So every year that we came up with some ideas. What if you have extra limbs into certain locations? It creates all interesting things. And then actually, seeding work,
At the Massachusetts Institute of Technology, robotics researchers are developing ways to add an extra pair of arms to your body.
The robot will try to act according to what I'm doing.
Robotic arms come to life thanks to artificial intelligence. The AI system monitors the wearer's arm movements, and eye trackers detect where the person is looking. From this data, it predicts the next movement of the wearer and automatically moves the robotic arms to a supporting position. No explicit human input is needed.
yeah, maybe that's good enough. But then most exciting applications I found in this SuperLimbs, supernumerary robotic limbs is space applications. This is a 2023 IEEE Spectrum articles. So we can attach the pair of robotic arms to the life-saving unit in the backpack here, and that to substantially, increase the physical capabilities of the astronauts. So going back to the moon, astronauts must conduct quite an extensive physical work on the moon's surface, and that's actually being the big questions. And remember that the Apollo eras, astronauts, superhumans, the super athlete, but when there, they fell. And then once they fell on the moon surface, it's hard to get up, and sometimes more than 10 minutes they struggled. So this is the reality. So we propose, how about having the third arm and the fourth arm attached to their body? Yeah, this is the stowed positions, comes in here, and then when needed, it comes out to make a balance or bracing, or if necessary, it becomes actually, extra 2 legs, so the human becomes a quadruped instead of a biped. Well, that may be necessary in case you're moving in a very rough terrain. And then actually once they slip or fell, we actually assist them to come back. So this is the most recent machine that we developed together with the JPL. It's hard to get inside, but you see a pair of raw arms are coming out of it, and yeah, this is so it has a 4+4 and 8 degrees of freedom for 2 arms. And it produces plenty of torques to lift the in order to stop. Unfortunately, we haven't got the IRB approval, so I can't show you the real humans working together with this robot. So that's where we are. And interestingly, the work on the astronaut assistance and elderly care, they are so close, because once you wear this space suit is pressurized inside, you know that, right? And it's just very stiff. So astronauts have to work against that stiff joint. So the net, muscular, strength is very small. Also, the visions are very limited, right? And then balancing is an issue that they fall. The same story as we see the care. So fall is actually the big problem for elderly community, and many of them they underestimate the risk of fall. I'm okay, and then they fall, or they overestimate the risk. I don't think I can do that. So staying, sitting in a couch all day, stop taking any necessary exercise, that actually increases the risk of fall further, and then they fall. 1 in 4 U.S. citizens and older adults, 65 or older, on Ford, and then totally 37 Ford cases and reported. So we need to do something to support the elderly person to take a safe exercise. And this is a robot holding. Well, in case that she collapsed, she's young, but in case of the old person, the robot can hold. Or that this is actually a new version. It's almost a passive one. It moves together with this actually Tai Chi, exercise. Now, yeah, I know one of the most actually successful, I think, seems to me, device we have developed is so-called handle anywhere. So elderly person today do need some handle to grab, right? And typically you place in the bathroom like this. But fixing this handle rail on the this kind of wall, it's too far to reach. And it's not really useful. We wish to have a handle here, but there's no wall. You can't put it here. Well, that's not the case. And if you have something robotic solutions.
As people age, grab bars are commonly installed around the home environment to provide stability and support for everyday activities. However, grab bars are costly and constrained by the room layout, resulting in suboptimal handle locations. What if there was a way to put a handle where it would most support the body?
Oops, go ahead.
Enter Handle Anywhere, a mobile reconfigurable robot capable of positioning a handle to optimally support an elderly patient.
Yeah, so this is the new versions, E-bar, and then we extended the capability to much higher.
Including lifting a person, assisting with postural changes and ambulation, and catching a person during a fall, all without the use of any wearable device or harness. An omnidirectional, high-traction drive base enables the robot to translate and rotate in any direction to support natural human motion. Each wheel's orientation and velocity are controlled independently. The base maintains high grip with common bone surfaces to resist lateral forces exerted by the user. With a minimal width of 38 centimeters, the robot can navigate through obstacles in the home environment and has the ability to lift users across gaps such as a bathtub lid. A rapid two-stage inflation system builds 4 airbags to catch and stabilize the user during a fall in less than 250 milliseconds. The frontal airbags prevent the user from falling forwards. We developed a novel 1 degree of freedom, 18 team exertion of performing the task.
Yeah, this lady, our neighbor, volunteered to be a human subject here. She had the brain surgery some time ago, and every other month she slipped or near falling. So when she tried to reach some high locations, she had to hold something. And when she tried to reach some low part, and it's very dangerous. So she needs to hold somewhere there. So she needs something to grab and anywhere. That's a handle anywhere concept. So now handle anywhere, the project is going further. We are developing the new versions and virtually creating 3 grab points because sit to stand up process. So we try to find the best location for the grab bar, and then that's actually varies depending on the process. This is actually multi-phase in this the process, and then actually as a human stand up, the best location of the handle is different. So we have virtually 3 handles place or the place the places. I can't actually talk about the elderly care without talking about the collaboration with the Stanford, in particular, Prof. Alison Okamura's group, with a fantastic project that I very much enjoyed, and I learned a lot under the NSF Convergence Accelerator project as soft growing robot and mobility assistance. And this guy, well, everyone knows her groundbreaking, new work on the application of BindBot. And in this case, it's actually going beneath the person lying on the bed. And so, it's easy to lift up the person because the sheet is already there in place. Before this, we have to do this kind of stuff. Two caregivers roll the patient on each side and spread out this sheet before lifting. So this is very much, laborious process. The two persons who need it. It's much better to do this, Okamura BindBot that can actually do this, very quickly. So let me see. I just talk about the many things. So how are you doing? This okay? Any clarifications and questions up to this point? Okay. Okay. So let's move on to the second half. Yeah.
On sale.
That's actually I heard, so show this to the national people. Can I buy it now? Oh, well, this is still the research phase. So, we are actually, my students formed in a company, and then it's not actually this form, but putting together something to deliver the stuff to those people who desperately need it anytime soon. Okay, so let's move on. So the next topic, well, that is actually back to that sit to stand program. I said it's going through multiple stages, and first, moving forward, creating a momentum. It is actually converted to uprise motions, and at the end, we just arrive at the stable positions. Kind of a feedback control is working. We don't know when and how the feedback control kicks in, but there's some very smooth transitions. We don't know what's going to happen. So we found that the humans are very good at something controlling multimodal things. And so this is so-called switched dynamical systems. And many of the hard robotic programs, it's basically related to switching of the dynamic systems. So gait walking, you see that the kind of change of the modes, one leg contact is basically open kinematic change, and you have two legs and closed kinematic change. Totally different dynamics are switched. We don't know exactly how they switch, but there's something going on. Also, the manipulation, breaking, making contact, changes the dynamics, and there's something that we should explore in that. But it's actually a hard problem. But each dynamic mode is governed by the different dynamic equations. We can simulate this process, but it's hard to gain the global picture. What's really going on, and actually, come up with some feedback control. Oh, that's a hard problem. So what I like to propose is to use the Koopman operator as a mechanism for unifying, otherwise segmented and switched dynamical systems, and then subsuming all the actually segmented dynamics within a globally linear model, which is obviously very amenable for controls. So this is kind of strange things because each dynamics is a nonlinear, like this kind of nonlinear dynamics, and putting all together, and then actually writing one equation, which is actually globally linear, A, something plus B something input. This is just a standard, linear systems state equation that you learn, right? So, once we can actually transform this one into this form, we can use any kind of, rich, linear control techniques, analysis control techniques that can be applied to this, including model predictive control that can be applied to this. It turns out that this optimization is convex optimization, and that's very actually efficient in the real-time computation. And I want to show you this to applying to both locomotions and manipulation. Locomotion, well, this is the limit wheel, and then pushing and shoving. And then if time permits, I'd like to talk about the sit to stand transitions. That's actually human neuromotor control program. So first, let me describe how this one can be, reduced to this form. There are certain conditions the system must satisfy, and then that is something I'd like to explain. The first of all, Koopman operator is very mysterious, and then I think some of you already know it, but let me, just to bear with me, I'd like to explain this in a very simple and intuitive manner, so that everyone can understand the basic principle behind it. So let's consider the nonlinear dynamic system to discrete time. F is a function to mapping xt to xt plus 1. Now, also we consider a set of orthogonal, also normal basis functions, phi 1x and phi 2x and as such. Okay, and the Hilbert space, don't bother the Hilbert, So we consider the composition of the basis function phi I with the self-map, actually this state transition functions f. So what this means is that we replace the x here by this function the f of xi, and then we write it phi I small circles and the capital F. Okay, this is a new function, and this function has kind of good properties involved in the Hilbert space. If that's the case, this new function can be expanded to a series of orthonormal the basis functions of phi I. So if you feel a little bit uncomfortable with this equation, you can think about the kind of finite dimensional vector space. So this is the vector, and that can be decomposed to two components here and here. This is a unit vector. So projection to this given by this is kind of an inner product between this guy and this guy, right? Which is sitting here. And then in the directions of phi I in this here, and to take a summation, you can recover the original function, right? So if this bracket means the inner product in the case of functions, kind of an integral. But anyhow, if you're a little bit uncomfortable with that, you can think about just the trigonometric functions and Fourier series expansion. Trigonometric functions is basically orthonormal basis of functions, and you can expand the sum function Sx into this form where Cn is a constant, and then that is actually basically integral in a product between these functions and basis of functions, right? So everyone knows this. So this is something, doing this. But this is a very important expression. Just to keep in mind that this guy is to be transferred to the next line. So here, left-hand side, in left-hand side is phi I small. This is the compositional functions, and then what inside is actually phi of fxt, and fxt is basically a state of transition functions. So what this means is basically xt plus 1. This guy. So this one really means that the values of the orthonormal function, the directions, evaluated at the next time and t plus 1 state xt plus 1 equals so this guy is the phi j and the xt, right, multiplied by weighted by these coefficients, which is actually constant, and then we can put it in the aij. So what this means is that the next step of the state phi t plus 1 viewed from your new coordinate system, which is actually orthonormal. We put all these elements into this, making a big matrix, vector, which is infinite dimensional. It's given by this coefficient aij times actually this current the time xt's states, the big ones, and in between you have this matrix aij. So this one is linear. We started with nonlinear, but this is linear. So I see that here's a very complex nonlinear system here. That's these basic the functions. It's a kind of functions of original state X. So it can be viewed as output functions or something you observe, right? So if you have many friends and each having the different eyes, viewing the same nonlinear system from the different angles, they will put together everything. It looks like a linear system. Wow, this is kind of interesting. So this is where we are here. I started with the orthonormal functions to begin with, but it doesn't have to be. It actually, you can use any basic functions that span the Hilbert space. Then we can do that. So we can very much relax these conditions, shown here. Now, so this is actually original Koopman operator theory. Unfortunately, this is applicable only to so-called non-autonomous system, autonomous systems with no control input. So, no control, no use, and what we are interested in is something that you have, control terms over here, right? So first, job I did was to expand this, autonomous Koopman to non-autonomous Koopman by putting it into this guy. This is a hard problem, but I know the idea is the following. So this is already, this is the full nonlinear state equation xt plus 1 f of xt ut, and this is not actually the form, where the the Koopman operators are applicable. So we do some special treatment. First of all, we divide the independent state xt into two parts. One is actually state variables, related to actuator side. The Qt is all the other things, the plant side. So we divided into these two, and then we we assume that this input ut terms, shown up here in this nonlinear equations in a linear form. BP is constant. We found in many systems that this kind of a linear control terms can be found. So once we found this kind of a relationship, we can apply the Koopman in the same way as the original form. First of all, we first get rid of this, the terms, and then actually work out the autonomous system. This is a standard Koopman, operator problem. We can reduce this one into this high-dimensional, linear form. And then after that, we can just simply, superpose that the linear, control terms. The proof is a little bit more, involved, but that's all you need to know. More importantly, the conditions under which this method is applicable is that the control input appears linearly in the actuator dynamic model. So this is the modeling property 1. And then also, a lot of the important things, the actuator and the plant, have independent state variables. So to satisfy these two conditions, let's look at the just a standard robotic systems where we have motors and the gearing that oftentimes harmonic drives used, and then actually arm load, right? So if we include the harmonic drives compliance, which is somewhat significant, the joint displacement and then the motor axis displacement can be treated as independent, generated coordinates, so independent variables. Okay, and also, if you put together the equation motions of this motor, since motor rotor inertia is constant, so input side is to appear in here is linear. So to satisfy that, we found the similar things in the hydraulic and the pneumatic, the soft robotic systems too. And also interesting is to look at the bio and the mechanical muscle systems too, having a nice springs in there, and then that allows us to apply the Koopman models. Okay, so let's look at the locomotion problem. The simplest model that we like to look at is a rimless wheel. So rimless wheel is actually mimicking some of the human gait like this in the simplest form, but we just push it a little bit further to make it actually active. So in this case, 6 spokes, 6 legs having an independent actuator, pushing this legs, changing this spoke lengths. So looking at the coordinates to describe this hub, and we have x, y, and then theta, and three the coordinates, along with the spoke lengths, generated by the actuators, in this case, 6 spoke lengths, basically generate the coordinates. Are they independent to each other? Well, they are airborne. It is airborne. Absolutely, they are independent. But if they are in contact with the hard surface, actually, there's some conflict happens. X, Y, theta side and the phi side cannot actually dictate their positions independently. They have to conform to some constraints. So that kind of a conflict occurs. But if you consider some compliance at the floor or this like a spoke, we can resolve that kind of a conflict. So compliance is very important in here. And in the leg, actually, research community, they have been studying the compliance of the foot and the floor for years. And we just pick up the best one in there and put together the actuator side of the dynamic equations. Although this actually ground directional force is a highly nonlinear term to ground directional force, but if you look at the actuator dynamics equations, all the inertia reflected to actuator axis is Im, it's linear and constant, and then actually actuator torque applies in here. So because Im is constant, actuator input is introduced in here and linearly. Even though this part is non-linear, that's okay, and they appear as linearly. So actually having this compliance here with this dynamics, and we solve the proof problems. One is that actually the Koopman operator can be applied because of these two independent variables, and actually switching between no contact to contact is basically not discontinuous because of this compliance. So these two support the applications of Koopman method. So again, that this actuator side of dynamics can be reduced to this in a linear form here, along with the nonlinear terms. And the hub side of dynamics is governed by this actually ground directional force is highly nonlinear, but there's no direct channel from input to UI to this dynamics directly. So that to satisfy the the conditions, and then we can build the Koopman model. So interestingly, this is the linear model. So we apply this one to model predictive controls, and using the kind of a penalty for tracking the deviations and the penalty for the control cost, subject to linear dynamic equations along with some other linear constraints. We can solve it very simply. So looking at the time horizons, it goes to some actually state contact contact state transitions, but we can foresee along this time horizon different modes of contact can be predicted. So if you have a kind of let me show first let me show this nice videos by my student Jasmine Terrons. So in here it is it defines how to actually move forward, and when trying out this, and then MPC controller finally discovered the way to coordinate the multiple axes moving forward. We're not actually given any other information. That is a the cost of performance to optimize. No other information is given to this. So it goes closely in the different contact domains. So boundary existing. If you just take actually the Taylor expansion type of linear approximation here, you have no clue about once it moved to these regions, right? No information about it. But Koopman, because it's globally linear and then subsumes all dynamics, it knows what's going to happen after you make the transitions like this. Of course, this works when you can foresee certain time horizon. If time horizon is very short, it can't actually cannot actually discover the right actually on on the schemes. And expanding the time horizon 12, okay, very beautiful. 8 is very, we can make it. Now let's look at the manipulation. So this is actually non-printhead manipulation by Cormac O'Neill. And so this is sort of a state of the art, I would say, about several years ago by my colleague, François Hogans and Alberto Rodriguez. They did a beautiful job, manipulating this, but I have to assume that this one is code static, and the contact must be maintained all the way through this. But my human interest going to this, right? Humans much more the dynamic, kicking the stuff, sometimes dribbling something, shooting. Yeah, that's what we want to do. How we can move up to that point. Well, we did it with this simple robot. This UR5 having a pretty good and high fidelity velocity control. So actually commanding each X and Y axis, moving at the specified velocity UX and UI. And then this, resultant position is simply just integrations of these two. So actually treating all this as an actuator dynamics, input the UX, UI as linearly, involved in this actuator dynamics. And then the PX-PY integral is the state, variables involved in the actuator side. Now, this actually, put, on the object side, slider side, we have the 6 state variables, X, Y, D, and their time derivatives. Are they independent or not? We have to actually include some kind of compliance, and then we intentionally use some compliant on the pusher like this. So actually, this, the indentation into this is to create the force in proportion to this in the displacement. That's the system to the modeling we did. So with that, we have to first model this, and then the next one, a big one, is that we have to create these basis functions. I said it's called an observables. What sort of functions can do the very good job in doing that? And we use the deep neural net and providing some data, the data-driven systems. It defines the best set of basis functions or observable functions, because it has to be in a finite state, and depending on the quality or effectiveness of such functions here, sometimes convergence is very slow, and sometimes it's very good. So neural net is very effective in finding that kind of stuff. So with this, we formulate the Koopman models, and then going to implement implementations. So this is the just a few results. So task is to move this board and here the slider from this point to this positions. And the initial position of the pusher, this guy, the robot, the pusher, is here. So you can't actually pull this guy towards this direction. It's only pushing the side, not pulling right. So MPC controller, find a way of doing that. First, detach from this surface, move to this point, and then start pushing it in this way. So that's actually the kind of control strategy discovered by the MPC together with the Koopman model. So it's really the dynamics, and then also I have to say that it is very much reactive. When you disturb this, and actually it can react to it very quickly, because it is basically faster computation, we found it almost 100 times faster than the traditional computations. Because and you see that the average the time cycles is 5.3 milliseconds. And we set the goals about the 10 milliseconds, it's much lower than that. I said almost 100 times faster than its traditional counterparts. Traditional counterparts in this case is to compute this program. It's basically kind of a hybrid thing, so you have to switch over this. And it turns out to be a mixed integer nonlinear programming program. And that is notoriously difficult to compute because you have to select which one is in the state. And that's actually integer s, and it must be optimized. That means that the contact sequence must be optimized together with the whole this the details optimizations. So compared to that, 100 times faster. And also this reactive, so disturbance can be treated very nicely. Now, another very interesting point I'd like to mention is that it can switch between dribbling and shoving or kind of shooting. We did not touch anything in terms of the basic structure of the systems, but shown here is that we just tweak this tracking error and penalty and the Q is increased, and then reduce the control cost so that the big motion is allowed in here. And it turns out that the UR5 is find that the new goals far from here. Then what happens is that switching the mode from just dribbling to a big shooting, that happens. We did not do anything special, but just setting up these parameters there, the system can actually find the best strategy in reducing this given cost. So this after this point, you may feel that this is too good to be true, or I'm showing the only champion data, right? But in fact, we did a very thorough parameter studies. It's not just good luck things. And first of all, one parameter which is very much questionable is the flow of friction. So sliding here, what is the friction between this? It's really actually hard to estimate, right? So if the friction is properly, correctly estimated, it actually shows a very precise dribbling here, even though a little bit actually disturbance comes in, it's a very accurate dribbling. On the other hand, if the real friction is much lower than the the values used for computation, it tends to overshoot. So things are more erratic. Although because of the feedback control, it can manage this, but an error is very big. So one techniques we found very effective. We call that the friction aware, the deep Koopman network. We include the friction quotient mu as actually additional kind of state given to this, and we train the neural net for the very different for the old range of friction mu. So this is a larger scale Koopman operator than the with a single mu. In the real time, we do some kind of parameter estimations, and effective mu is estimated at the point, and then actually put that estimated mu value in here. That is evoke the particular Koopman matrix A associated with that particular mu. So thereby we can actually make it adaptable to the original program. So yeah, this is the plotting plot of the squared error versus friction. And yeah, first of all, no friction adaptation is made. It's pretty actually large error is happening. If the friction is very large, and it's not a matter, but very slippery, isolating type of things, we got the big error. On the other hand, we apply that friction aware deep neural net, and knowing the, right friction, make adjustment, we lower the, error quite significantly. And another very important thing is that I'm pretty sure that some of you raised some question. We, so far the formulation is highly hinged on the compliance involved in, right? So, what happens if the compliance is very low, very stiff one, you may have the trouble in here, right? Does it impact the Koopman prediction accuracy? Is there any fundamental limitation to that? So we did some kind of a parameter study, and that is shown here. So vertical axis is prediction error, and the horizontal axis is stiffness. Scale and logarithmic scale and stiffness is shown. And please look at the blue line. Accuracy is pretty low, so it's good. And then from certain point it jumps, extremely high stiffness. We had the trouble in actually estimating the actions. Yeah, so there's some limitation to it. Now look at the other side. Suppose that push-out compliance is very soft, very, very soft, too soft. What happens is that you have to push a lot. You have to make a longer actually distance travel to create the force, right? So that turns out you get the quite a significant phase lag in doing this. So we took the reciprocal to that resonance frequency as a kind of a surrogate of this controlled authority, controlled fidelity, and that shows up here. Too soft is not good. There's some kind of sweet spot and somewhere here, which is actually good in both senses. And then we look at the overall MPC control performance, trajectory of cost. Then there's actually kind of a band between here and here. It's actually very nice. Get the excellent control performance. So the story is that yes, we have some limitations, but think about this compliance as a design parameter. Yeah, you can pick the compliance at the tip of whatever. Yeah, so that the overall control performance will be maximized, optimized. So this is kind of flipping the questions, but we can make it actually, on the best, from the control viewpoints. So I've been talking about this stuff, and then finish the locomotion and manipulation. And if time permits, I just briefly talk about the neuromotor control, sit to stand transitions. And here, modeling the sit to stand transition. As I said, it actually goes through at least 4 different discrete modes of motions. This is actually trajectory, experimental trajectory, solid line. Trajectory of the center of mass of the human subject, moving from here to this point. And then we apply the following techniques. So first of all, human body is treated as a triple inverted pendulum. So this is just a robotic case. And equation of motions can be written in this form, where unfortunately the joint torques here multiplied to some coefficient, which is actually configuration dependent. So in this form, the Koopman operator method cannot be applied in its form. But if you look at the muscles, interestingly, muscle has nice compliance. And then we actually model that actually the dynamics. And then it turns out that the muscle dynamics, looking at individually, it can be treated as independent state variables. And then some nerves signals can be treated as a new input to the system, which shows up linearly in the system. So with this, we can successfully formulate the Koopman model. And to this, we designed a linear quadratic regulator. And this is a kind of state of feedback K multiplied to this to actually, improve the response. And it turns out that this actually motions, experimentally obtained the trajectory can be actually simulated by tweaking, by the optimizing the parameters involved the linear quadratic regulator. Remember that's actually four different, very different stages of dynamics all mixed together in one equation, and which is linear. So we can apply this, LQR, algorithms. So just a quick summary. Yeah, I introduced the Koopman operator as a mechanisms for unifying otherwise segmented dynamics and subsuming individual local dynamics within a globally linear model. And then I go through the kind of physical modeling under which this global linear representation is possible. And then applying the MPC, and it basically made a breakthrough from my viewpoint because before it's so hard to do real-time control for MPC. Now it's possible. And then more interestingly, viewing the kind of transitions, after going to different regimes, it can foresee what's going to happen. So based on that, MPC controller can discover some elaborate control strategies, even though we did not actually do any spoon feeding, guiding them to certain solutions. Very simple one, it made something possible. So I see that the Koopman operator can serve as a catalytic operator, given some domain knowledge or on equation motions or experimental data. Yeah, we applied the Koopman operator together with the machine learning things to find the best basis functions or observables. And the end result is a globally linear, unified model, which is very much amenable for estimation and control, and the real-time and convex optimizations are possible. So Koopman can be treated as a general framework for solving robotics, on the challenge and beyond. Now, this slide is most actually debatable, but let me tell you something. So this is a kind of an interesting accomplishment, I displayed it today. Now, talking to neuromotor scientists, along with the Koopman research community people. Well, as far as actually human behavior is concerned, it's so complex that we can't actually make any kind of a good explanations. But it is conceivable. It is conceivable that the human dynamic body control motion like this actually, while the receiver catching the ball, now where he has actually eyes and then make adjustment in such a dynamic environment. Or soccer players dribbling this and just seeing the other opponents, right? It's hard to believe that the human is doing some complex and nonlinear optimizations. Maybe dynamic predictions is very similar in the linear domain, but I know for years of training and experience, the difference is that in this part. So they know what are critical variables, what's very informative, important variables through some bunch of experience and training. And then at the end, they have all informative set of variables, and then making some dynamic transitions. It may be linear, and then the computation afterwards is so simple because of this form. So this is nothing but the conjecture that there's no way to prove it, right? And maybe then in the next 50 years it's necessary to put some probe and then actually find, oh, here's the Koopman. That may not happen, but it's very much likely that such complex things may be coming out of very simple things. And otherwise actually very difficult to do. So I just have to acknowledge my group. It's so much fun working with these guys and the gals. And here's my sponsor, Natural Robotics Initiative, and SFCMM, and NASA, and such. Thank you. That's all about it.